In today's session, I'm going to discuss a problem which is called as all pairs shortest path problem, which can be solved by using dynamic programming approach. So you already know the basics of graphs. So you'll be given a graph, a directed graph and a weighted graph, which will have a set of vertices V and a set of edges E, where the number of vertices in the given graph are n. So you'll start by constructing initially an adjacency matrix, and these are the rules for building an adjacency matrix. For example, consider this graph, and I'll assume that this is the graph, a directed graph with the paths. There are 3 nodes and there are 2 edges, and each of this edge is associated with a weight. Now, if I'll have to build an adjacency matrix for this, an adjacency matrix records the distances between the nodes. And now, the adjacency matrix will be an n by n matrix. It will be an n by n matrix. So here the number of nodes are 3. So this will be a 3 by 3 matrix. There will be 3 rows. And there will be 3 columns. Now I'll have to fill this matrix, which is called as an adjacency matrix. And this adjacency matrix specifies the distances between the nodes. Now always in an adjacency matrix, the diagonal elements values will be zeros. That is, you can see this rule here. The distance between the node to itself is always 0. The distance or the cost from ith node to ith node, it is equal to 0. So I'm going to fill all the diagonal elements here to zeros. Then I'll have to fill the remaining spaces. So for that, any value in the matrix gets into either case A or it gets into case B. If I take any 2 nodes I and j, and if there is no direct edge connecting I to j, then the value should be filled up to infinity. I'll repeat again. I consider any 2 nodes, ith node and jth node, and if there is no edge connecting ith node to jth node, then that particular value in the adjacency matrix should be infinity. If there is a direct edge connecting ith node and jth node, then the cost of that edge should be filled up into the matrix. So I'll start filling up the remaining values in the matrix. Now I'll try to fill up the distance from node 1 to 2. I'm going to fill up the distance between node 1 and node 2. So it falls into case A. It falls into case A because between the first node and second node, there is a direct edge connecting these 2 nodes, and hence the value in the adjacency matrix must be the cost of that edge, which is connecting node 1 and node 2. So now I'm going to fill up 4 here at this place. This is because there is a direct edge connecting 1 and 2. Now I'm going to fill the value for this location, which is adjacency between node 1 and 3. So if you observe the figure, the graph, there is no direct edge connecting node 1 to node 3. So it falls into case B, where the value in the adjacency matrix must be filled in as infinity. Then next value, I am going to consider node 2 and node 1. Node 2 and node 1. This is the value that I'm going to fill up. This is the value that I'm going to fill up. Now this value is either infinity or the cost of the edge, depending upon whether there is a direct edge or not. So for that, I'll check node 2 and node 1. I'll check whether there is a direct connection between these two edges. So I will consider that this is a directed graph and there are arrow marks here. The edges are directed. So I'll consider some arrows here. This is a directed graph. So now if I check, I can traverse from node 1 to 2, but I cannot traverse from node 2 to 1 because the edge here is a directed edge. So now I can say that there is no direct edge between node 2 and node 1. So I'm going to fill up an infinity here. Then I'm going to fill up this place, which is adjacency value between node 2 and node 3. Again, if I see the graph between node 2 and node 3, there is a direct edge and the cost of the edge is 5. So I'm going to fill up 5 here. So I'm going to fill up a 5 here. Now, I'm going to consider third row. Third row, first column. Is there any direct edge between node 3 and node 1? No, it is not there. So I'll fill it up with infinity. Is there any direct edge between node 3 and 2? It's not there. So I'll again fill this as infinity. This is what is called as a cost adjacency matrix that you are going to build as the first step in solving a given problem. So this, how to fill up, you should be able to know it. So once you have the problem and the adjacency matrix, the all pairs shortest path problem is to determine shortest paths between every pair of nodes. This is every pair of nodes. This is not edges, but this is nodes. You'll have to find shortest path between every pair of nodes. That is, if you have, say, for example, this particular graph, the all pairs shortest paths problem is to determine paths between every pair of nodes. That is, you have to find shortest path between node 1 and 2, node 1 and 3, node 2 and 3, node 2 and 1, node 3 and 1. So between every pair of nodes that exist in the graph, you have to find the shortest path, and that challenge, that problem is called as all pairs shortest path problem. And for that, we are going to construct a matrix. And this matrix A is going to present the shortest paths, the lengths of the shortest paths between every pair of nodes in the given graph. Now for that, we are going to use one of the algorithms, which is called as Floyd-Warshall algorithm, for finding the lengths of the shortest paths between every pairs in the graph. Now, the restriction, if you want to use this algorithm, there is a restriction that is posed on the graphs, and the given graph G should not have any cycles with negative length, with negative cost. That is the rule. The given graph G should not have any cycles with negative cost, and then only you can apply this Floyd-Warshall algorithm on such graph G. Now, the Floyd-Warshall algorithm works like this. For example, you have an ith node and a jth node in the graph, and you already know one path between I and j. You already know that there is one path between I and j. For example, I am taking some node 3, node 4, and say for example, there is some node 7. These are the ith node and the jth node in the graph. And there is a direct edge connecting these two nodes whose weight is 9. I already know this path, that there is a direct edge connecting node 4 to node 7, the ith node to the jth node. But I have to also explore the other paths. Maybe the other paths that are there might be shortest paths. That may be giving me less cost than 9. Because this is not greedy algorithms that we are talking about, but we are talking about dynamic programming where all the choices will be explored to choose an optimal solution. All the possible choices will be explored at each step to come up with an optimal solution. Maybe, even though there is a direct edge connecting node 4 to 7, maybe there is another path which is connecting 4 and 7 via an intermediate node k. Via an intermediate node k. So this is ith node and this is jth node, and k is an intermediate node that is connecting ith node to jth node. And maybe if you explore and check the length of this path or the cost of this path, maybe less. So the cost of this another path is 3 plus 4, 7. The cost of the second path is 3 plus 4, it's 7. And the cost of this path is less than the direct edge. So that means between 4 and 7, if you have two paths, this path is the shortest path. So as such, there are two paths now. There may be another path where there is more than one intermediate edges, and the path of the cost of this path may be still less. So you can see that if you take this particular path, the cost of the path is 3 plus 1, 4, 5, 6. It's still less. So what you are going to do is, once you find a path, a direct path between I and j, a direct path between I and j, you are going to explore other paths which involve an intermediate vertex k. And you are going to find out whether this path which leads from I to j via k may be shortest. And for that, the I to j path via k, if it has to be shortest path, then I to k path must be shortest and k to j path must be shortest. And if this is taken care of, then such an algorithm is said to satisfy the principle of optimality. The principle of optimality says that the sub-solutions of an optimal solution must also be optimal. If there is an optimal solution, main solution, and it has some sub-solutions, then those sub-solutions must also be optimal. So if you apply the same principle of optimality here, if I to j path must be optimal, then I to k path must be optimal and k to j path must also be optimal. That is, the path from I to k must be shortest and the path from k to j must be shortest. Then only the entire path I, k, j will be shortest. then only we can say that principle of optimality holds. So our algorithm, Floyd-Warshall algorithm, takes care of such situations, and hence it is said to satisfy the principle of optimality. That means whenever an algorithm satisfies principle of optimality, whenever a problem satisfies principle of optimality, then dynamic programming approach can be used to solve the problem. So this is Floyd-Warshall algorithm. Initially, we are going to build an adjacency matrix as the first step. The first step is to build an adjacency matrix, A naught. This is what is called as A naught. You are going to build A naught. Then in the remaining steps, you are going to build remaining matrices, which are called as A1, A2, A3, and so on. So how many number of such matrices you are going to continuously build? That depends upon how many number of vertices are there in the graph. If there are 3 vertices in the graph, then you are going to build A1, A2, and A3. If there are n number of vertices, then you are going to build A1, A2, and so on up to AN. And for this, in each step, when you are building A1, when you are building A2, in each step, you are going to follow this process. I to j, there is a direct edge maybe, there is no direct edge maybe, but what you are going to do is between I and j, to find the shortest path, you are going to first consider and select an intermediate vertex k that falls between I and j. This intermediate vertex k may fall between I and j, it may not fall, that we'll see later. But whenever you want to construct a shortest path from I to j, you are going to select an intermediate vertex k, and then you are going to try and find 2 shortest paths, I to k and k to j. You are going to find 2 shortest paths from I to the intermediate vertex and from intermediate vertex to j. If you are able to find those 2 paths and you are going to find that it is a shortest path, then we are going to update the matrix. So for that, let us try to work on a problem. So before working on a problem, you'll need to know a small technique when to update a distance matrix, when you should not update a distance matrix. This is one of the steps in Floyd-Warshall algorithm, which says that in case 1, you will not update the distance matrix value between I and j. The distance between I and j, you will not update the value. Otherwise, case 2, where you are going to update the value of the distance between I and j. When you have to update, when you should not update. For that, I'll give you a simple example so that you will understand what is this formula. So for that, see this graph, take this graph. There are 3 nodes, 2 edges which are weighted edges. So now I'll try to represent the distances between the nodes and assume that this is a directed graph, and I'll start filling up the distances. The distance from 1 to 1, the distance between a node to itself is always 0. Then what is the distance between node 1 and node 2? There is a direct edge connecting node 1 and node 2. So the distance between node 1 and node 2 will be 4. Then find out what is the distance between node 1 and 3. There is no direct edge connecting node 1 to node 3. So that will be considered as infinity. I'm taking only node 1 as a source, and I'm trying to find shortest paths from node 1 to 2 and node 1 to 3. So this is your initial distances. Now, what I'll try to do is, because there is a direct edge from 1 to 2, we'll leave it. But there is no direct edge from 1 to 3. So what can I do? I have to pick an intermediate vertex. So I'll take that. This is the intermediate vertex. Now, when this is an intermediate vertex, now you have to find out distances from I to k and k to j. And you have to add the distances. Now, what is the distance from I to k? I is your node 1. K is the intermediate node. J is node 3. Now, what is the distance from I to k? From node 1 to 2? It is 4. And what is the distance from k to j? It is 5. So here, distance from node 1 to 2 is 4. From there, it is 5. So I'm going to have these parts, find out the cost, add it, and the value is equal to 9. Now check whether if this 9 is less than infinity. So the infinity is nothing but the current distance of node 3. Check if the new distance I to k plus k to j, if it is less than the current distance value of node 3. If it is so, if it is true, that means I'm going to replace this infinity value with 9, because now I have found out a shortest path whose value is not infinity. And how did you find this shortest path between node 1 and 3? Via an intermediate vertex k. Right? Now I'll start writing the formula. And the formula is, if you want to find out the new distance, if you want to find out the new distance from some node I to some node j, then you have to find the minimum values among two values. What is the minimum value among the two values? What are those two values? The first one is, what is the current distance of node j? So for that, you'll write a of k minus 1, which is the current distance between node I and node j. This is one value, which is your infinity value. Now, how did I get 9? I added the distance between ik and the distance between kj. So for that, the second value will be a of k minus 1. The distance, the current distance between the nodes ik plus the current distance between the nodes kj. Now you have two values. This is your first value, the current distance between ik plus the current distance between kj. And this is the current distance between I and j. These two values you find out. Whichever is the minimum value, that will be the new distance value from node I to node j. So this is the formula. And these are the two cases when you are going to update the distance between ij, when you are not going to update the distance between ith node and jth node. Okay, so we'll start working out a problem. So there has been given a directed graph. It's a weighted graph where each edge is associated with a weight. And the problem given is you have to apply Floyd-Warshall algorithm to obtain all pairs shortest paths. And the result, this solution will be in the form of a matrix. It will be in the form of an n by n matrix. Now, this is the given graph. As I said, you'll have to first start by building A naught, or in some textbooks, it will be given as D naught. Anyway, both are same. So I'll start with building D naught. So I'm going to build the initial adjacency matrix, which is called as D naught. Now, what will be the size of this matrix? This matrix will be a 4 by 4 matrix because the number of nodes in the graph are 4. There are 4 nodes in the graph. Now, so there will be 4 rows and there will be 4 columns. So what did I say? I said that initially fill the diagonals with zeros. Yes, I am going to fill up the diagonal values to be zeros because the distance from a node to itself will be 0. Once this is done, the remaining values I have to fill up. I'll try to fill up and check what is the distance between node 1 and 2. If there is a direct edge between node 1 and 2, then you'll take the weight of that edge and place it in the matrix. Otherwise, you'll place an infinity value in the matrix. So I'll start filling up. There is a direct edge from 1 to 2 with cost 0. So I'm going to put a 0 here. The distance between 1 and 2 is 0. Then distance from 1 to 3. Check. Distance from 1 to 3. There is no direct edge from 1 to 3. So I'm going to fill an infinity at this place. So I'm going to fill here an infinity. So observe the graph. I'll start filling up the remaining values. Distance from 1 to 4. There is a direct edge between 1 and 4 with value 5. 2 to 1. The distance is 4. 2 to 3. There is a direct edge with weight 2. 2 to 4. There is no direct edge, so I'll place an infinity. 3 to 1. There is a direct edge with weight 6. 3 to 2, there is no direct edge. 3 to 4, there is a direct edge with weight 1. 4 to 1, the distance is 7. 4 to 2, there is no direct edge, so the value will be infinity. 4 to 3, there is no direct edge, so the value will be infinity. So this is your initial adjacency matrix or initial distance matrix, which is called as D naught, and this will be your step 0 in the Floyd-Warshall algorithm. Step 0 is you have to formulate the initial distance matrix D naught. So the initial distance matrix D naught, what I have filled up, it has come like this. So whatever I have filled up, this was the initial distance matrix I took, and D naught I formulated like this. This is your step number 0. Then we'll move on to step number 1. Step number 1, step number 2, and so on. Now, how many number of steps this has to repeat? Now, how many number of distance matrices further after D naught, how many more distance matrices you are going to build? So building D naught is mandatory. After that, the number of distance matrices you have to build is equal to the number of nodes in the graph. There are 4 nodes in the graph. So I'm going to build D1, D2, D3, and D4. Now always D1 matrix is built based on D0. D1 is built based on D0. D2 is built based on D1. D3 is built based on D2. D4 is built based on D3. So D0 you are going to build using D0, you'll frame D1. Then using D1, you are going to frame D2 and so on. So I'll start building distance matrix number 1. Now D1, why I am calling it as D1, that number 1 indicates which vertex you have to consider as intermediate vertex. If you are building D1, the intermediate vertex is first node. If you are building D2, the intermediate vertex will be second node. So now you understand, when you are building DK, the intermediate vertex will be the kth node. Now this is my D0. From this D0, I am going to formulate D1 by considering first node as the intermediate node. And for that, the first thing that you have to do while building D1, because first node is the intermediate node, you have to take row 1 and column 1 from D0 and fill them as it is into D1. You understand my point, isn't it? So while building D1, the intermediate vertex is the first node. So while building D1, the first thing that you have to do is go to D0, take row 0 and row 1, fill it as it is row 1 and column 1, and fill it as it is into D1 matrix. Then fill diagonal elements as zeros. Diagonal elements will always be zeros. So fill those parts also. Then start filling up the remaining parts, remaining values. So this was D0 till now. Whatever we have filled up, this is your D1 matrix. I have filled directly row 1, column 1, directly from D0. Then I have also filled diagonal values with the zeros. Then remaining values I'll have to fill up. Now, I'll start filling up this value. Fill up this value. That is the distance between 3 and 2. The distance between 3 and 2. Now check D0. What is the current distance between third node and second node? The current distance between third node and second node, it is infinity. Okay, keep this value. Now, also find out, so you have found out that the current distance between third node and second node is infinity. Now, what is the intermediate node here in D1? First node is the intermediate node, that is k is equal to 1. So what I have to do is, now I have to find the paths and distances from 3 to 1 plus 1 to 2. I already know that there is some path between 3 and 2 whose distance is infinity. Now I'm considering an intermediate node which is k equal to 1. The first node, I'm considering it as intermediate node, and I'm checking whether the path from 3 to 2 via 1, is it shortest? It may be shortest. So that is from node 3 to node 2 via node 1. I am trying to check, is there a shortest path? So now check, what is the distance, current distance from node 3 to 1? So node 3 to 1, the current distance is 6. Okay, so that will be your 6. Plus, what is the current distance from 1 to 2? Current distance from 1 to 2 is 0. Now, 0. Now, infinity, and you have got a value 6. This is the current distance. This is the new distance from 3 to 2 via 1. Now, whichever is minimum, you are going to fill it up here. You are going to fill up the value here, whichever value is minimum. Whether the current distance between 3 and 2 is shortest, or whether the new distance via node 1 is the shortest. Find out, and accordingly you are going to fill. Now, what did I do? I have filled up a 6 here. Now I'll try to fill up this value. That is the distance between 4 and 2. Now, what is the current distance between fourth node and second node? It is again infinity. This is the value, infinity. This is the value that we have taken. Now, I'll try to find out what is the distance between 4 and 2 via intermediate vertex 1. So for that, I'm going to find out these values. Current distance between 4 and 1. Current distance between 4 and 1, which is 7. So this is 7. And what is the current distance between 1 and 2? It is 0. So that is 7 plus 0. Between these two values, the current distance and the new distance via node 1, whichever is minimum, that I'm going to fill it up here. Right, now trying to fill up the value here, which is 4 and 3. Between 4 and 3, between 4 and 3, so between 4 and 3, this is the value, current value. And the new values between 4 to 1 and 1 to 3. 4 to 1 value is 7. 1 to 3 value is infinity. So current distance is infinity, and the new distance is 7 plus infinity, whichever is less. So anyway, this value will be retained as infinity, because 7 plus infinity will also be infinity. So as such, filling all the remaining values, you are going to get this matrix. You have got this D1. Now from D1, you are going to build D2. While building D2, the intermediate vertex is node 2. Now this is the D1 that we have built. Now from this D1, we are going to start building D2. The first step is take second row, second column, second row, second column. From D1, as it is, fill it up into D2. We are taking second row, second column, because in this step, the intermediate vertex is 2. Now, as usual, fill up the diagonal elements with zeros. So I have filled up diagonal elements with zeros. Now fill up the remaining values. So for remaining values to fill up, I have to fill up the remaining values from D1 to D2. So what are all the remaining values that are there? We'll see. So I'll start filling up. I'll fill up this value. and that value is distance between node 4 and node 1, distance between node 1 and node 3. Now, what is the current distance between node 1 and node 3? It is infinity. So this is infinity. Now, try to find out distances from 1 to 2 plus 2 to 3. So that is, you have to find the distance between 1 and 3 via intermediate vertex 2. Okay, so for that, what is the distance from 1 to 2? 1 to 2 is 0. Distance from 2 to 3, it is 2. So this is 0 plus this is 2, which is equal to 2. Now, among these two values, infinity and 2, which is minimum value, that I am going to fill it up here. That is how I got this value 2 in the matrix. Now, finding out how I got this 5 here. So for that, I'm going to take distance between node 1 and 4. The current distance between node 1 and 4 is 5. You can see that here. Node 1 and 4, the current distance is 5. Now you have to find out distance from 1 to 2 plus distance from 2 to 4. That is, you have to find a distance from 1 to 4 via node 2. So 1 to 2, it is 0. 2 to 4, it is 9. So you have to consider the current distance from 1 to 2 and 2 to 4, which is 0 plus 9, which is equal to 9. Now you try to compare the current distance with the new distance. Whichever is minimum, you try to fill it up here. So now I'm filling up a 5 here because that is the shortest distance. That is, the direct path from 1 to 4 is the shortest path. The path via second node is long path. So I'm always going to consider the shortest path. So as such, you will fill all the values. You'll get D2. From D2, using D2, you are going to build D3. While building D3, the intermediate vertex will be 3, and you'll follow the same procedure as in the previous steps. Then again, using D3, build D4. While building D4, the intermediate vertex will be the 4th node. Build D4. Then this will be the end of the process because we have 4 nodes in the given graph. So we have to build distance matrices up to D4. So we'll stop here. Now this D4 is the matrix that presents to you all pairs shortest paths. All pairs shortest paths. That is, the distance from node 1 to itself is 0. The shortest distance between node 1 to 2 is also 0. The shortest distance from node 1 to 3 is 2. Node 1 to 4, the shortest distance is 3, and so on. So from every node to every other node in the graph, these are the shortest distances. Okay, so this is Floyd-Warshall algorithm. We have worked out a problem using Floyd-Warshall algorithm, which uses dynamic programming approach to solve all pairs shortest path problems. So D4 matrix gives the all pairs shortest paths in the given graph. So this is the algorithm. all paths, which takes two inputs, cost matrix, the initial cost matrix, and the number of nodes in the graph. How many number of nodes are there in the graph? There are n nodes. And the initial cost adjacency matrix D naught, that will be the inputs for the algorithm. The output will be matrix A, which presents to you all pairs shortest paths. So this is the initialization part where you are going to build A naught or D naught. The initial adjacency matrix is copied as it is into D naught. Then once D naught is ready, you are going to build D1, D2, D3 and so on up to Dn. So for building the remaining distance matrices, these are the loops. You'll have to use 3 loops. This is because you have to build n number of matrices, D1 to Dn, n number of matrices you have to build. And for that, for building D1, D2, D3 and so on, this is the loop, kth loop. Then in each distance matrix D1 or D2, there are number of rows and there are number of columns. There are n rows and there are n columns. So in each distance matrix, this ith loop is for number of rows and jth loop is for number of columns. So I have taken 3 nested loops, and hence the time complexity of this algorithm is big O of n cube, because there are 3 nested loops. The time complexity of the algorithm is big O of n cube. And the formula that I have used, this is the new distance between ith node and the jth node. The new distance between I to j is the minimum of the 2 values. And what are those 2 values? What is the distance, current distance between ij, and what is the current distance between I to k and k to j? Calculate these 2 values, find the minimum value, and that will be the new distance from ith node to jth node. And repeat this process for every row, every column in a distance matrix, and as such you are going to build n number of matrices in n cube time. That will be the maximum time. So instead of writing big O of n cube, you can also write theta of n cube. So this session I have discussed what is the all pairs shortest path problem, and given a graph, how do you apply Floyd-Warshall algorithm to find out all pairs shortest paths? And finally, I have now presented to you the algorithm and its time complexity. So this was all pairs shortest path problem.